Hey guys, yesterday we were taking a look at vectors, and we were looking at vectors geometrically, and today we're going to look at them algebraically. So here's an example of a vector that we would have drawn yesterday. The last class, whenever I drew these, I would count like 1, 2, 3, 4, and then 1, 2, 3 to figure out how the vector was moving, and then I could translate that onto the grid. Well, that movement, that 1, 2, 3, 4, and 1, 2, 3, is a way to algebraically reference a vector. So I could call this vector 4, 3. We use these little, they're called chevrons. They're kind of like pointy parentheses. Down here, you can probably see a better example of that. But that ordered pair that you're looking at is actually the movement of this vector. The vector goes over 4 and it goes up 3. Kind of reminds you of slope a little bit because we're talking about the movement of this line. Okay, and that is an algebraic representation of a vector that talks about the horizontal and the vertical components of how this thing moves. On the next page, if I get that lined up, you'll see an example of this vector right here. This is in what's called standard position. It's anchored at the origin and then is moving from there. You'll see that it ends at the point 3, 5. Well, if it starts at the origin and ends at 3, 5, then that point is actually how this vector is moving. It goes over 1, 2, 3, and then it goes up 1, 2, 3, 4, 5. Okay, so that is vector 3, 5. You could also think of this as the result. Okay, this is something we did yesterday. If you had a vector that was traveling just 3 that way, and you had another vector that was traveling just up, this is the resultant of those two forces. This vector plus this vector equals this vector. That's going to be important in a minute. Okay, so this is vector 3, 5, but all of these could be referenced as vector 3, 5. Okay, because that just talks about the movement. So if a vector is positioned at the origin, if it's in standard position, then that terminal point will be our algebraic representation of a vector, but any vector anywhere in space could be referenced that way as well. So the problem is we're not always going to have a picture where we can just count 1, 2, 3, 4, 1, 2, 3, whatever. Okay, so we need if we're talking about these geometrically, we need a geometric formula that'll find the vector for us. Well, that's what this is. So this little formula, what do we need? We need to know how our vector is moving horizontally. So what's the change in our horizontal movement? And then what's the change in the vertical? Well, that's what this formula is. x2 minus x1. So take your terminal x and subtract your initial x. And then y2 minus y1. So take your terminal, what y value does it end at, and subtract the y value where you started, and that'll be the change. Well, those values should probably look kind of familiar to you. This is just the slope formula. Okay, y2 minus y1 over x2 minus x1. But it's written as an ordered pair instead of as a fraction. That's it. So if I have some point in space, I could graph it, and then I could count, but we'd really rather not do that. If I have a vector PQ, so it's starting at P and going to Q, so this is my terminal point, this is the terminal point, then this vector would be 6 minus negative 3, comma, and then 3 minus 1. So this is the vector 9, 2. Okay? All right. There is a second algebraic way to look at vectors, and that's the thing we're going to talk about next. And this is used a lot in like physical sciences, like engineering. Engineering will talk about vectors this way. And it's by using what are called unit vectors. So first let me explain what that is. A unit vector is a vector that is 1 unit long. If that vector is traveling horizontally, we use the letter I. So this is a horizontal unit vector I. For if that unit vector is traveling vertically, we use a J. In a lot of sciences, you'll actually be looking at things 3D, And so you would have a vector that's coming out of the page at S, and that would be vector K, so ijk. But we're not gonna do that. We're gonna stick with 2 dimensions. Okay? So if this is the algebraic, like ordered pair way to talk about the horizontal and vertical components of a vector, this is writing the vector as the sum of these unit vectors. So let me give you an example. So let's say we've got the vector 3, 2. Now you can probably picture that. That's a vector that's traveling 3 to the right and 2 up, which means using unit vectors, it's traveling 3 unit vectors in the horizontal direction. So there's 3 i's. So 1, 2, 3. To approximate that last one. And then we're going to add 2 of these vertical vectors. So 1, that's j, and that's another j. But I'm adding them together. So my result is this vector, which is the vector 3i plus 2j. So we can write vectors as the resultant of these unit vectors. Okay? Now, if you do that, then we've got some formulas on how to add and subtract, multiply vectors here. So, given unit vector form, so ai plus bj and then ai plus bj, I'm going to add these 2 vectors together. All you do is you combine like terms. Okay? You add the horizontal vectors, you add the vertical vectors, and that's your new vector. Okay? To subtract, you just need to make sure you distribute the subtraction. You're going to take these i's, subtract these i's, but then you're going to take these j's and subtract these j's. Over here would be an example of writing the vectors in that ordered pair form. Again, if you're going to add vectors, you just add the horizontal components, you add the vertical components, and same with the subtraction. To multiply a vector by a scalar, so yesterday we would have vector v, and then we would draw 2v. Okay, so we would multiply it by 2. Well, all you need to do is make sure you distribute that multiplication, that both your horizontal and vertical components are going to get stretched by that amount. The last thing, the thing that we didn't do geometrically, is we never found the magnitude of a vector. The magnitude is the length. Well, geometrically, we would have needed rulers, and we really didn't want to do that. So, now that we have an algebraic way, we can find the magnitude of a vector. This is the symbol for the magnitude. Looks like kind of a double absolute value going on there. Okay, but it's just the Pythagorean theorem. Okay, so now that we're talking about these vectors in kind of a horizontal, vertical component or an x, y component, we can just use the Pythagorean theorem, and then we can tell how long the vector is. Okay? All right. Let's look at these examples right here. I've got 2 vectors, v and w. I want to add those 2 vectors together. Okay? So I'm going to add their i's, 8i. I'm going to add the j's, plus 3j, and that is my new vector, 8i plus 3j, that I do not have to draw. I didn't have to draw anything. I just had to add their parts together. Okay? To subtract, make sure you're distributing. So the 6i, we're going to subtract 2i. But then the negative 2j, we're going to subtract 5j. So negative 7j. For c, what is 5 times v? Well, the last class we would draw v 5 times and then connect all that, and that's 5v. Well, we're just going to take v and we're going to multiply everything by 5. So 30i minus 10j. And that's not something we could have drawn yesterday. Yesterday we were limited to this small little grid, and we had to kind of keep things in the grid, or close to in the grid. But now we can take a look at any vector anywhere and multiply it by whatever we want to. Okay? For d, I would probably do that in parts. I want to take 2 times v. Well, 2 times v would be 12i minus 4j. And then I want to subtract 3 times w. So 3 times w is 6i plus 15j. And then I need to combine these. So 12i minus 6i, negative 4j minus 15j, and that's my answer. Now, right here, I subtracted and I distributed the 3. I could have also connected that negative to the 3, and I could have distributed it in one shot. I could have distributed the negative and the 3. So negative 3 times 2 would be negative 6, and then negative 3 times 5 would have been a negative 15, and then I would have added things together, and I would have got that same answer. Okay? E. E says, what is the magnitude of vector v? So this is vector v. It is the absolute value of 6 squared plus negative 2 squared. So that's 36 plus 4, so 40, which, don't plug that in your calculator. If you did, I wouldn't be upset, but I would just probably write that as 2 radical 10. Okay? Now, last one here, F. I've got make sure you understand what this is saying. It's saying, what is the magnitude of v plus w? So, we need to find what v plus w is. And then we're going to find the length of that new vector. Well, we actually already found v plus w. We found it was 8i plus 3j. And now I need to find the magnitude of that. Okay, so it's the square root of 8 squared plus 3 squared. So square root of 73. And like I said, I would just leave it like that. That's a fine answer. Okay? All right. Now, if I can talk about a vector, some vector as its horizontal and vertical components, I could also talk about a vector in terms of how long it is and at what angle from the origin that it's going. Well, that'd be polar form. And that's the last thing we're going to do. We're going to take a look at what's called polar form of a vector. So, right here, this is the magnitude. That's our r that we're used to finding. Okay, what's the radius? How far from the origin? Well, that's what magnitude is. It's how far from your starting point are you. And then cosine A is your horizontal direction, and sine A is your vertical direction. So cosine of alpha, or theta, whatever you want to do, okay? Cosine alpha I plus sine alpha j. So this is using that unit vector form, but it's in polar. So look at the example. This is write the vector in standard form given the magnitude and the direction. So we're just going to plug these in. So 6 cosine of 60i plus sine of 60j. Hardest part for some of you is going to be not confusing this with the complex numbers, where we had an imaginary I right here. This I is different than that I. Okay, this is a unit vector. That's a unit vector. For the other ones, it was an imaginary number. Okay, so plug the values in and then just simplify. Cosine of 60 is 1/2, so there's going to be an I there. Sine of 60 is radical 3 over 2. There's my j, and then distribute it. 6 times 1/2. 6 times, well, again, that 2 and that 6 are going to reduce. So 3 radical 3j. And that's your answer. Okay, try B. Try to do B. So plug the numbers in. I want you to do it. I'll keep working it, but I'm going to stop talking. And then when you get done, please look at my final answer and make sure both of these are negative. Okay? 225 is in quadrant 3. Both sine and cosine are negative in quadrant